The topic of today are advanced principles of sound level measurements. And the background of this webinar are numerous questions from our customers who have been asking us over the past time about the backgrounds and the applications of the various sound level measurements that are supported in the XL2 acoustic analyzer. We will actually refer at some points to this instrument, but this is definitely not a product presentation, but we really want to focus on the theoretical backgrounds of these sound level measurements. My name is Markus Becker, and sitting next to me is Bruno Nix, our product manager, who will assist me during this webinar, and he will be also answering your questions. The topics that we have prepared for you start with an overview of different level terms and definitions. Then we will dig a little bit deeper into the corresponding terms and explain how they are calculated and measured and what they are used for, summarizing these explanations, and followed by some application hints for long-term measurements and recordings with the XL2 analyzer. And at the end, we will at latest answer your questions and provide some auxiliary information. The duration shall be in the region of about 30 minutes for the presentation. Well, let's start with the level definitions, and here you see the formula for the live level. I will not dig too deep into this formula. Just the capital letter of L stands for sound level, that you're going to see again at many times. And the next value actually, which is closely related to the live level, is a very important one, the equivalent continuous level. You see the major difference between these two values is here in the equivalent continuous level we have an integral, so that means that we are averaging the live level over the recording period. So whereas a live level gives us an information on the instantaneous status, the LEQ gives us the information of the averaged level at the end of our recording period. The next level is also related, the maximum level. This is actually the maximum live level that has occurred during the recording, during the measurement period. And I'm going to show you that in a graph just on the next slide. But first, there's an important information, and these three values are all RMS values. RMS stands for root mean square, which is a measure for the power of the incoming signal. Secondly, you may have noticed this P0 value here, which is required for the logarithmic calculation, and the P0 is the reference sound pressure level, and that has been defined by 20 micropascal, which is approximately the human hearing threshold at 1 kilohertz. And then you will encounter during your work, but also during this webinar at some points, the terms A or C or Z. These are frequency weightings or fast, slow impulse or time weightings. These terms will not be explained in detail in this webinar. We have done that in a previous occasion that we can watch on our website if you like. So there's a recording for that previous webinar. Today we will focus rather on the levels without these weightings. The next level we shall take care of is the peak level. This is not an RMS value, that's an important issue, and I will explain you the difference between peak level and maximum level just in a minute. Then we have the interval level, which is basically an expression that you record or you display a level result that has been recorded over a defined interval. And the percentile level, which is statistical analysis, will also be explained in more detail later. So let's start with the live and the equivalent peak and maximum level. First of all, just to remember, how do we measure, how do we calculate these results. We have a sound source, a sound pressure level coming onto the front of our microphone capsule. This capsule translates this sound pressure into a voltage. The voltage is then sampled and digitized, and then the signal processor calculates the required results out of this digital data stream. An important side note is that the microphone sensitivity, which is the ratio between the microphone translates the sound pressure level into this voltage, this microphone sensitivity goes, of course, also into this calculation. That's very important because we need the scaling so that the end result is really accurately representing the physical situation in front of the microphone. So this is a schematic example of such a microphone voltage. These sketches that I'm going to show you and the graphs I'm going to show you in this presentation are rather schematic. They are intended to illustrate the basic principle of this calculation and measuring method, so they are not scaled exactly as you can see here or mathematically 100% exact. The intention was to give you an understandable example of this procedure. So the output voltage of a microphone capsule is an AC voltage, and the first thing that we do is we rectify this AC voltage, which means that we flip the negative half waves to the positive side, to the upper side of the graph, and that we do by squaring this signal. And of course, as we said before, we also scale it together with the microphone sensitivity. So this gives us the rectified result, the rectified sound pressure level signal. And this is already the first measure that we can use here for the peak measurement. The peak is an indicator of the maximum rectified level that has occurred during my measurement, and peak max means that the displayed result, which is represented by this dark green dotted line, the displayed result will always stay where it is unless an even higher peak occurs. And then again it stays up here to the end of my measurement unless there is even another higher peak. And maybe you notice the Z. Z means unweighted, so for this example I have no frequency weighting, but important is L, peak, and max stands here for that the displayed result will always represent the maximum peak level that has occurred during the measurement. The next step is to calculate the RMS result out of this incoming signal, and RMS root mean square, there is a root included, and this has of course the consequence that the RMS values will always be smaller, will be below the peak values. And this is a very good database now for our maximum level display, because we just have to look similar to the peak level, but now for the RMS value. So here the right hand scale applies. Where is my maximum RMS value that has occurred? Again, the displayed result stays at this value unless it is overruled by an even higher value. But only the pink points will be considered for the L max, Z again for unweighted for the L max display. And then we have the LEQ result, the equivalent continuous level. You remember that was the average result. So here into this purple dotted curve, all the levels over the whole history up to the corresponding point go into the calculation. So you see it comes up here, then it becomes a little bit more horizontal. There's another smaller peak due to this one, but due to this previous time, there is not an immediate response as for the instantaneous level. The LEQ is always an averaged integrated result, and depending how the signal continues, if there are no more incoming signals, it would slowly go down again. One more side note, which is very important: the peak value will always be higher than the max value for the reasons that I explained to you. How does it look in practice? We can see here the sampled input signal from a microphone capsule. Now we have a sampling rate of 48 kilohertz, which means that 48,000 samples per second are required. The first step, you remember, was to rectify the signal. So we flip the negative parts below this zero line to the positive side. So this would look like that. And then it wouldn't make sense to display 48,000 results per second. Nobody could ever follow that. And even if you log that to a file, this would really boost your database. You could not really do something reasonable with that. So for that reason, in a first step, we group these samples into segments and we calculate the corresponding results here per segment. The green dots, for instance, represent the live level per these segments, and if I connect them, I would get a curve that represents my live level over time. So an important side note is that all the samples within these segments will of course be considered for the corresponding calculations. And if I would now look for the peak or for the maximum level, I would of course also consider these peaks. So there is no information getting lost in this process. It's just a kind of an aggregation process to reduce the information to a reasonable amount. But as you can see here, if you look at the time axis, we are still in the millisecond range, and this is far too fast to be displayed on an LCD or to be logged into a file when you do a long-term recording. And for that reason, there is even another aggregation happening afterwards. So these data that you see here are just used internally by the test instrument. So what would you do for a long-term recording? And that is actually what we see here. This is a practical example of a long-term recording, the very first few seconds of that recording. And what has been adjusted here is a log interval of 100 milliseconds. And that means that we are recording this live level and we are summarizing the result every 100 milliseconds. So for instance, here this purple curve is the LAEQ dt, and dt stands now for the fact that the LAEQ, the A-weighted equivalent level, has been calculated for each slot of 100 milliseconds. And you can see that this is a very good indicator for what is happening. Apparently here, the very first seconds, the sound pressure level was rather low. Then we had a first peak, and we can see that immediately. Then it was a little bit more silence again, and then some more peaks. So the LAEQ dt is a very good and much more stable indicator for what has happened than if you would display all these live levels in milliseconds interval. That wouldn't make any sense. Now we can overlay this graph with the LAEQ. And you remember the LAEQ is calculated for the whole period, not just for the logging interval. So we start at the exactly same point as the LAEQ, but then the development has a much higher inertia due to this integrating, this averaging procedure that is applied. Only here this very high peak implies a kind of a jump of the LAEQ as well, but then again it stays quite stable again. So this, you can see that this LAEQ follows, of course, the overall average behavior of the sound pressure level that is present during the whole recording period. Another important thing I would like to explain to you is the difference between repeated LEQ measurements and gliding LEQ measurements. What you see here is a graph from a musical recording with a logging interval from 1 second. So we are having actually a time frame of about 2 hours in front of us. You see down here all the samples, thousands of samples that have been recorded. The blue curve is the LAEQ dt, so the equivalent level per log interval. So what we do now, if we do a repeated measurement, we define a time period, for instance 15 minutes, during which we record the LAEQ, and then we reset it. And let me show that to you. This is the red line representing the repeated LAEQ. So we start recording the LAEQ, as you have seen in the picture before, but then at the end of this time window, we reset it and start from scratch again. You can see that here very clearly. For instance, there was a silence, a short silence apparently, and there was a reset at the same time. So the LAEQ was up here by considering what has happened in here, but then after reset, it was very silent and it restarted down here. The same, by the way, applied here. So here was the end result of this 15 minutes, a reset, and during this pause, the LAQ was apparently following this very silent environment before it was reset again, and so on. And in opposition to the repeated LAQ, I'm going to explain you now the gliding LAQ. This is the green curve. How do we get there? Let's assume we are at this point here of our musical. So what we do is we apply again a time window, but this time window has no fixed position. It continuously follows our recording. So we just always consider the past 15 minutes of our recording, and we calculate the LAQ, that's the result for this time period, out of the data that we have acquired here within. So that is the basic difference between the fixed slots of the repeated LAQ and the gliding time window of the gliding LAQ. Then some words about the percentiles. Percentiles, as I said, is a statistical analysis, and to start I would like to explain you the meaning of the L50. L50 means 50% of my recorded samples within this time window, that's the one I look at, 50% of these samples are above this value. The green line represents the L50 value, and 50% of my samples have been higher than this value, and the other 50% have been below. In the mathematical language, we would call this a median value, but we can also explain it that you can say during 50% of the time within this period here, during 50% the sound pressure level was higher than this value, and during the other 50% it was lower. Well, we can calculate the percentiles, of course, also for other percentages, like for instance the L90, which stands for 90% of my samples are above that line, or L10, which could be interpreted that during 10% of the time the level was higher than the corresponding value, or the L1, which is something very close, very similar to the Lmax, which is representing just 1% of the samples that have exceeded this value. So this is quite a good indicator for the maximum peak, for the maximum level that has occurred during my measurement. On the opposite, the L95, by the way, is a very commonly used value for background noise. So when you do an environmental measurement and you calculate the L95, then you have a very good reference for the background noise of the location where you have been. You can see that here on this screenshot, which we have taken from our Data Explorer software. Here, this is the table with the different percentile results. You can edit this table in terms that you can add more values if you want. Here, for instance, you see the L95 that I have mentioned before. That would be a good indicator for the background noise, and L1, this is almost the maximum level that has occurred during my recording. And here you see the statistical distribution. These green bars represent the number of occurrence, or the percentage of occurrence, for the corresponding sound pressure levels that are plotted here on the x-axis. The blue curve is the cumulated frequency of occurrence for the corresponding sound pressure level. So nothing, no value above 90 dB has happened, whereas 100% of the recorded sound pressure level has been higher than 49%. So let us summarize these levels that I have explained to you, starting with the live level. Two examples, LAF and LAS, are instantaneous levels. There's one disadvantage with these live levels, and that is that they are continuously following the incoming sound, and that results typically in a quite quickly fluctuating result display. I'm going to show you that briefly. This is here an XL2 instrument that I have connected to my PC, and where you see the content of the display. So this is actually my voice that is being measured by the instrument, and you can see the LAF is jumping up and down. It's quite difficult to say where is about the average or what was the peak value. It's an indicator what is happening right now, but it doesn't give us really long-term information. Then we have the LAF max and the LC peak max that I have explained to you. So that was the highest RMS value, the highest rectified value that has occurred since I started my recording. And here the LAEQ is a very stable one. That gives me the average level of my voice in this room. So if I clap into my hand, you see immediately the LAF max, the LC peak max jumped up. Maybe you saw something here, but this is really hard to follow. And here the LAQ was almost the same, so the impact of my clap was very secondary over this recording period. You see that down here of over 20 minutes. And that gives us already some valuable information for the levels that frequently or normally have to be measured in specific applications. The LAEQ is a very popular measure to quantify environmental noise, but it's also used in live sound applications, concerts or discotheques. However, it's not a must to record this value. The important point is definitely the national standards, the national legislation in your country, which tells you for which application which measurements need to be executed. So please make yourself acquainted with this standards, with this legislation before you start a measurement. You have to know the purpose of your measurement, of course, and then you have to look up in the standard what measurements, what weightings need to be applied to be on the correct side. I showed to you the LAQ DT, which is the LAQ per time interval. It's a very nice measure to analyze the development, what has happened during a long-term event in more detail. Then we have the maximum and the peak level, which are required by different national standards, again, depending on the application. And we have the percentiles that give us a good statistical measure for instance, assessing road traffic or community noise. Some application hints for the XL2. First important point is you need to verify whether the microphone sensitivity is set correctly. If you are using a microphone from NTI Audio, this is not that much of a hassle. You just have the sensitivity saved within the microphone, and this information is automatically transferred to the instrument. So the XL2 will always know exactly the correct sensitivity of the connected microphone, and it will use this information apparently to correctly calculate the measurement results. Next point is you need to activate the logging. Here in the logging menu, you have to activate this mode, and you have to select the logging interval. The minimum interval is 100 milliseconds. That is a good choice for industrial noise, machinery noise analysis, but you can adjust that also, for instance, to 1 second, which is a good choice for longer monitoring applications, or you can even increase it to more seconds, to minutes, even to hours. The log interval, as I have showed to you, is the interval by which the accumulated measurement results will be saved in the log file. The next step is to select the measurement function, the measurements, the level measurements and the weightings that are necessary for your application. Again, please notice the national legislation in your country for doing that. And optionally, you can add the spectra to the recording and even an audio file recording. This is a very helpful feature. For instance, if you in the post-processing are discovering that there have been some high peaks during your recording, you may program the instrument in a way that it records a sound file of these events, and so you can listen to them, you can identify what has happened exactly in that moment. Next step are to adjust the input range of the instrument. If you are in a very silent environment, you should select the lower scaling, so it goes down, for instance, here to 10 dB, and this makes sure that you are accurately measuring even very silent environments. Whereas in the opposite case, in a very loud environment, you would adjust the range to the upper maximum to make sure that no clipping occurs. Sorry, that was one too early. And you should also adjust the recording mode, for instance, continuous mode or repeated. Repeated was the one that I presented to you before. And the final step is to press the start key to make sure that the measurement begins in that moment. If you want to know more about this whole procedure, please notice that we have had a webinar on this topic recently, and this webinar is also available on our website. So if you want to see a guide, a stepwise guide through these setup procedures, you may watch this webinar. Well, I'm at the end of my presentation. I'm going to look at your questions just in a minute. But before, is there anything that comes to your mind after the webinar has ended, please do not hesitate and contact us. On this map you see the NTI subsidiaries worldwide, but we have many more partners in the important countries and very skilled, competent partners who will be happy to assist you, or of course you can always also contact us directly. And as mentioned before, you see down here the link where we will publish the webinar recording.